I woke choking on smoke for the third time that night, my eyes burning, my throat raw from coughing. The fire in the center of the tipi was small, barely a dozen sticks, but the smoke filled the entire space, thick and white, refusing to exit through the smoke hole at the peak. Outside, the March wind hammered across the northern plains, gusting to 40 miles per hour, driving the smoke back down every time it tried to rise. I'd crawled outside twice already to adjust the smoke flaps, the triangular canvas ears at the teepee's peak, but nothing I did improved the situation. This was my first night sleeping in a Lakota teepee, spring of 1867, camped with a band traveling north toward the Powder River country. I'd lived in army tents, in canvas wall tents, in every kind of temporary shelter the frontier offered. I thought I understood portable structures. A teepee was just a conical tent, I'd assumed, bigger than most, more elegant perhaps, but fundamentally the same, a canvas cover, over a pole frame, a fire inside for heat, a hole at the top for smoke. How different could it be? Very different, as I was learning through painful experience. The smoke wouldn't exit, the wind kept shifting direction, and every adjustment I made seemed to worsen the problem. I'd positioned the smoke flaps to block the wind. Logical, I'd thought. But that trapped the smoke inside. I'd opened them wide to let smoke escape, but wind poured down through the opening, driving smoke into every corner of the teepee. I was fighting the wind, trying to overcome it, and I was losing badly. Maka Washte, good earth woman, watched my struggles with patient amusement from her side of the teepee. She was perhaps 60 years old, a widow who'd agreed to let me observe and document teepee construction and use in exchange for helping with camp work. She'd raised her teepee in less than an hour that afternoon, a feat that seemed impossible given the structure's size, 18 feet in diameter at the base, 18 feet high at the peak, using 17 poles each 20 feet long. I'd helped her lift the cover onto the frame, stake it down, and adjust the interior furnishings. The process had seemed straightforward, almost simple. Now, in the middle of the night, with smoke burning my lungs, simplicity was revealed as illusion. Maka Washte rose from her sleeping robes, wrapped a blanket around her shoulders, and stepped to the fire. She didn't adjust the smoke flaps. Instead, she moved to the teepee's interior wall, a separate canvas liner that hung from the poles several feet inside the outer cover. She adjusted this liner, pulling it tighter in one section, loosening it in another. Then she repositioned one of the poles supporting the liner base, creating a wider gap between liner and outer wall on the windward side. Within minutes, the smoke began to clear. It didn't happen all at once. There was no dramatic moment when suddenly everything worked. But gradually, steadily, the smoke found its path upward and out. The air near the floor cleared first, then progressively higher, until only a thin haze remained near the peak. The fire burned brighter, drawing better, consuming the wood more completely. Within 10 minutes, the teepee was comfortable, breathable, warm. I watched Maka Washte return to her robes, settle in, close her eyes. She hadn't spoken, hadn't explained what she'd done or why it worked. But she'd demonstrated something crucial. I didn't understand this structure at all. What I'd dismissed as a simple tent was actually a sophisticated system, and I'd been operating it with the wrong mental model entirely. I lay awake the rest of that night watching the smoke rise cleanly through the hole at the peak, watching the fire burn steadily without filling the space with fumes. The wind continued gusting, shifting direction every few minutes, yet the smoke managed to exit regardless of wind direction. Something about the teepee's design, something I hadn't recognized or understood, was managing airflow in ways that shouldn't be possible with a simple conical tent. At dawn, I asked Maka Washte if she would teach me, not just how to adjust the smoke flaps or position the liner, but why the teepee worked, what principles governed its operation, how it could function in conditions that defeated my understanding. She agreed on the condition that I stop thinking of the teepee as a tent. A tent was a static structure, she explained through a translator. A teepee was alive, breathing, responding to wind and fire and weather. If I wanted to understand it, I had to observe how it moved, how it changed, how each element worked with the others. I spent the next 10 days living in that teepee, measuring and documenting every dimension, every detail, every technique for managing smoke and heat and airflow. What I discovered challenged every assumption I'd brought about portable shelter, about the relationship between structure and environment, about what was possible with canvas and poles and careful design. The teepee wasn't just a tent, it was a convection engine, an airflow management system, a dynamic structure that turned wind from enemy to ally. And the double wall, the liner I'd barely noticed, was the key to everything. The second morning, after a night of clear air and good sleep, I examined the liner carefully for the first time. I'd noticed it during the teepee setup, a semicircular piece of canvas that hung from the lodge poles about 5 feet above the ground, creating an inner wall around most of the teepee's circumference. I'd assumed it was for insulation, a dead air space between inner and outer walls to slow heat loss, similar to double wall construction in buildings. But when I measured the gap between liner and outer cover, I found it was 6 to 8 inches wide, far too wide for effective insulation, which requires minimal airspace to prevent convection. And the liner didn't seal at top or bottom. There were deliberate openings where air could flow. This wasn't insulation, this was something else. I asked Makawashte about the liner's purpose. She gestured to show air movement, down along the outer wall, up along the liner, and I began to understand. The gap wasn't dead airspace. It was a channel, a pathway for air circulation. The liner was directing airflow, managing how cold air entered the teepee and how it warmed before reaching the living space. I traced the air path starting from the bottom. The outer canvas cover was staked to the ground with wooden pegs, but not tightly. There was a gap of perhaps 2 inches around most of the circumference where air could enter. Cold air from outside would enter through this gap, drawn inward by the slight negative pressure created when warm air rose and exited through the smoke hole at the peak. Once inside, the cold air encountered the liner. The liner hung from the poles with its lower edge resting on the ground or slightly raised, creating a barrier that prevented the cold air from flowing directly into the living space. Instead, the cold air was forced into the gap between liner and outer wall. Being cold and dense, it flowed downward in this gap, seeking the lowest point. But the teepee floor wasn't level. It was slightly raised in the center where people sat and slept, sloping down toward the edges. The cold air pooled at the edges, in the gap between liner and outer wall, unable to reach the occupied space. As it pooled, it began to warm from contact with the warmer liner surface, from radiant heat from the fire, from the general warmth of the teepee interior. As the air warmed, it became less dense, more buoyant. It began to rise, still constrained to the gap between liner and outer wall. It rose along this channel, warming progressively as it ascended, until it reached the top of the liner at about 5 feet above the ground. At this point, the liner ended, and the warmed air entered the main living space, mixing with the warm air around the fire. The circulation pattern was a loop. Cold air entered at ground level, flowed down through the gap between liner and outer wall, pooled and warmed at the edges, rose back up through the gap, then entered the living space already warmed. The liner wasn't preventing cold air from entering. It was managing how that air entered, ensuring it was warmed before reaching the occupants. That afternoon I tested this understanding with smoke. I lit a small bundle of sage outside the teepee, near the bottom edge of the cover where air would enter. The smoke was drawn inward, disappeared into the gap between liner and outer wall, and reappeared several seconds later at the top of the liner, rising from the gap into the living space. The smoke trace confirmed the circulation pattern, down the outer channel, up the inner channel, into the living space. But why create this circulation? Why not just seal the bottom, prevent cold air from entering at all? I watched the fire for answers. The fire needed oxygen to burn. If the Tipi were sealed at the bottom, the fire would consume the oxygen in the living space, creating negative pressure that would pull air and smoke down through the smoke hole. That was exactly what had happened during my disastrous first night. By blocking the smoke hole with poorly positioned flaps, I'd prevented air from exiting, which prevented fresh air from entering, which starved the fire of oxygen. The liner system solved multiple problems simultaneously. It allowed air intake for fire combustion while preventing cold drafts from reaching the occupants. It pre-warmed incoming air before it entered the living space. It created a convection current that assisted with smoke exhaust. And it did all this passively, automatically, requiring no moving parts or active management once properly set up. I measured the liner dimensions precisely. It was semicircular, covering roughly 2/3 of the Tipi's circumference, the back and sides, but not the front entrance area. It was perhaps 8 feet tall and 30 feet long when laid flat, sewn from multiple pieces of canvas. The bottom edge was weighted with stones placed inside pockets sewn into the canvas, keeping it in contact with the ground and controlling the size of the air intake gap. That evening, Makawashte showed me how to adjust the liner for different conditions. On cold, calm nights, she weighted the bottom edge heavily, creating a tight seal that minimized air intake and heat loss. On windy nights, she loosened the weights on the windward side, allowing more air to enter the channel, increasing the convection current to help exhaust smoke. The liner was adjustable, tunable, responsive to conditions. By the end of the second day, I understood that the Tipi wasn't a single-wall structure like a tent. It was a double-wall convection system, with the outer wall protecting from weather and the inner wall managing airflow. The gap between them wasn't wasted space, it was functional space, as important to the Tipi's performance as the walls themselves. The third day, I focused on the fire pit and its position within the Tipi. In every tent I'd used, the fire or stove was centered, logical positioning that distributed heat evenly and minimized the distance from any point to the heat source. I'd assumed the Tipi fire would be the same, centered under the smoke hole, directly beneath the apex of the cone. But measuring carefully, I found the fire pit was offset from center by perhaps 18 inches, positioned toward the back of the Tipi, the side opposite the entrance. The smoke hole at the peak was also slightly offset in the same direction, creating a vertical alignment between fire and exit, but both were displaced from the geometric center. I asked Makawashte why. She gestured to show smoke rising, wind blowing, and the relationship between fire position and the liner's circulation pattern. Through a combination of gestures, limited Lakota words I'd learned, and patience, I began to understand. The offset position worked, with the liner's convection system. Cold air entered around the entire perimeter at ground level, but was directed by the liner into the channel between liner and outer wall. This air circulated around the back and sides of the Tipi, warming as it rose in the channel. When it emerged at the top of the liner, it was flowing from back to front, from the offset fire position toward the entrance. If the fire were centered, this air current would approach the fire from all directions, creating turbulent flow that would disrupt the smoke column. But with the fire positioned at the back, the warming air from the liner channel approached the fire from behind and around the sides, merging into a coherent updraft that carried the smoke upward in a stable column toward the smoke hole. The entrance, being at the front and having no liner, created a different air pattern. Cold air entering through the doorway when the entrance flap was opened would flow along the ground toward the fire, drawn by the fire's oxygen demand. This air would reach the fire from the front, be heated, and rise. The combination of back and side flow from the liner channel and front flow from the doorway created a converging pattern that concentrated into a strong updraft directly over the fire. I tested this with smoke visualization. With the fire burning steadily and the entrance closed, smoke rose in a tight, stable column from the fire to the smoke hole with minimal spreading or turbulence. When I opened the entrance flap, cold air rushed in along the ground, visibly disturbing the smoke column, but only temporarily. Within seconds, the smoke stabilized again as the converging airflows re-established the updraft pattern. The smoke hole position was also critical. It was offset to align with the fire, creating the shortest path for smoke to exit. But more importantly, it was positioned relative to the two smoke flaps. The adjustable canvas ears that controlled the opening. The flaps could be positioned to work with wind direction, creating a venturi effect that accelerated smoke exhaust. I climbed outside to examine the smoke flaps more carefully. Each flap was a triangular piece of canvas, roughly 3 feet on each side, attached to the teepee cover with a seam along one edge. The opposite edge had a pole pocket, a sewn channel that held a pole extending 5 feet above the teepee peak. These poles served as handles, allowing the flaps to be positioned from ground level by moving the poles. When both flaps were closed, pressed against each other, sealing the smoke hole, smoke was trapped inside. This was the configuration I'd created during my first disastrous night, trying to keep wind out. When both flaps were opened wide, extended away from each other like wings, the smoke hole was fully open, but wind could blow directly down into the tipi, disrupting airflow. The correct configuration, I learned, was asymmetric and dependent on wind direction. One flap would be positioned to block wind from one direction, while the other flap would be extended to create a low-pressure zone on the downwind side of the opening. Wind flowing over and around this extended flap created suction, the venturi effect, that pulled smoke out of the teepee more effectively than a simple open hole could. That afternoon, the wind shifted from northwest to northeast, and I practiced adjusting the flaps. With northeast wind, the southeast flap needed to be extended to create the low-pressure zone, while the northwest flap partially blocked the opening to prevent downdrafts. The adjustment took perhaps 30 seconds, and the improvement in draft was immediate. The fire burned brighter. Smoke exited more cleanly. By evening, I understood that the fire's offset position was part of an integrated system. The position worked with the liner's convection channel to create a stable updraft. It aligned with the offset smoke hole to minimize smoke path length, and it positioned the fire away from the entrance, preventing cold air inrush from disrupting combustion every time someone entered or exited. The fourth day brought variable winds, shifting direction every 10 or 15 minutes, gusting to 30 miles per hour, then calming briefly before building again. This was typical plains weather, Maka Washte explained. The teepee had to function not in ideal conditions, but in constantly changing conditions. Learning to manage the smoke flaps meant learning to read the wind, to anticipate changes, to adjust before problems developed. She showed me how to observe wind direction without instruments. Watch the grass, she indicated. It bends and shows which way wind flows. Watch smoke from other teepees in the camp. It reveals wind direction and strength. Watch the teepee cover itself. It moves and billows on the windward side, creating visible cues about which direction needs attention. But reading current wind wasn't enough. I needed to anticipate changes. She taught me to watch clouds, to notice when the upper air was moving differently than surface wind, a sign that direction would change. She taught me to feel pressure on my face, to notice when wind was building or dying. These weren't precise measurements, but they provided enough warning to adjust the flaps before smoke became a problem. The smoke flap adjustment wasn't binary, fully open or fully closed. It was continuous, with infinite positions between extremes. For northwest wind at moderate speed, the northwest flap would be positioned perhaps 30 degrees away from the smoke hole, creating a small windbreak, while the southeast flap extended 60 degrees, creating maximum venturi effect. For strong northwest wind, the northwest flap would close more, perhaps 15 degrees away, providing more protection, while the southeast flap might pull back slightly to prevent excessive draft. I practiced adjusting the flaps throughout the day, responding to every wind shift. At first, my adjustments were crude, too much movement, overcompensating. But gradually I developed feel for how much adjustment was needed, how small changes in flap position created significant changes in draft. The flaps were controlled by poles extending above the tipi peak, long enough to reach from ground level when you stood beside the tipi. Moving the poles required walking around the tipi to the correct position. You couldn't adjust both flaps from one location. This meant anticipating which flap would need adjustment based on approaching wind direction, positioning yourself appropriately before the wind arrived. That afternoon, I began to understand why the tipi's smoke management worked better than a tent's ventilation. A tent has fixed openings, maybe a peak vent, maybe a door that opens and closes. These openings can't respond to wind direction or strength. They work adequately in calm conditions but fail in wind, either allowing wind to blow in or trapping smoke inside. The Tipi's adjustable flaps transformed wind from problem to solution. Instead of fighting wind, trying to keep it out, the flaps used wind energy to enhance draft. A strong wind, properly managed with flap position, created stronger suction, pulled smoke out more effectively, improved combustion, actually made the fire work better rather than worse. The physics were straightforward. Wind flowing over an extended surface creates lower pressure on the downwind side, the same principle that creates lift on an airplane wing. By positioning the downwind flap to extend into the airflow, the tipi created a low-pressure zone at the smoke hole exit. Smoke, being slightly higher pressure than this zone, flowed toward the low pressure and exited more readily. I experimented with this by partially covering the smoke hole with a piece of canvas, restricting the exit area. Even with reduced opening size, if the downwind flap was properly positioned, smoke still exited cleanly. The venturi effect compensated for the smaller opening. This explained how the tipi could function in rain, closing the flaps. Partially to keep water out didn't trap smoke, because the remaining opening, when properly positioned relative to wind, still provided adequate draft. By evening, my hands had developed muscle memory for flap adjustment. I could feel in the pole's resistance how far the flap was extended, could judge the correct position without looking. When wind shifted, I automatically reached for the appropriate pole, made the adjustment, and returned to whatever task I'd been doing. The adjustment had become intuitive, reflexive, integrated into the rhythm of living in the tipi. Makawashte nodded approval. I was learning to listen to the structure, she said. The tipi would tell me what it needed, through smoke behavior, through fire performance, through the sound of wind on canvas. My job was to listen and respond, to work with the tipi rather than trying to control it through force. The fifth day, I attempted to map the complete airflow pattern through the tipi, not just the obvious flows I'd observed, but the entire circulation system from air intake through exhaust. I needed to understand how all the elements worked together to create the remarkably effective smoke management I'd been witnessing. I started with the intake points. Air entered at ground level around the entire perimeter where the cover was staked down. The gap size varied, tight on the back where the liner weights held the cover close to the ground, slightly larger on the sides, and largest at the front near the entrance where the cover was raised for access. Total intake area was roughly 6 square feet, distributed around the circumference. The entering air was cold. Outside temperature was perhaps 35 degrees Fahrenheit. This cold air was denser than the warm air inside, about 10% denser based on the temperature differential. Density differences create buoyancy forces, with denser air sinking and displacing lighter air upward. Once inside, the air encountered the liner. The liner directed the cold air into the gap between liner and outer cover, preventing it from flowing directly across the floor toward the fire. In the gap, the air was constrained, channeled, forced to follow a specific path rather than mixing chaotically with the interior air. I measured the temperature at various points in this channel using a thermometer tied to a long stick. At the bottom of the gap, where air first entered, 36 degrees. Midway up the gap, at 3 feet above ground, 42 degrees. At the top of the liner, where air emerged into the living space, 50 degrees. The air was warming progressively as it rose, gaining roughly 14 degrees through contact with the progressively warmer surfaces around it. The warming created buoyancy. The air entering at ground level was denser than interior air, so it sank and flowed downward in the gap. But as it warmed, it became less dense, eventually matching the density of the interior air, then becoming lighter. At this point, the air became buoyant and reversed direction, rising up through the gap. This reversal created a circulation loop. Cold air entered, flowed down in the gap, warmed, reversed, flowed up in the gap, and emerged at the top of the liner already warmed and ready to mix with the living space air. The liner was creating a heat exchanger, using the warmth of the Tipi interior to pre-warm incoming cold air before it reached the occupants. But the circulation did more than pre-warm air. It created a convection current, a continuous flow pattern that pulled fresh air in at the bottom and warm air out at the top. This current assisted with smoke exhaust by creating suction at the smoke hole, pulling smoke upward more effectively than fire buoyancy alone could achieve. I calculated the flow rate roughly. The Tipi volume was approximately 1,600 cubic feet. The fire consumed oxygen, requiring perhaps 20 cubic feet per minute of fresh air for adequate combustion. The convection current, driven by the temperature differential between inside and outside, created an exchange rate of roughly 40 cubic feet per minute, double what the fire needed, providing adequate ventilation for both combustion and breathing. The fire itself contributed to the convection. Fire produces hot gases, combustion products at temperatures exceeding 500 degrees Fahrenheit. These gases were dramatically lighter than the surrounding air, creating strong buoyancy that drove them upward. The fire acted as a pump, pulling air in at ground level and pushing hot gases out at the peak. The smoke column behavior revealed the flow pattern. Smoke rose from the fire in a tight column, indicating laminar flow, smooth, non-turbulent rising air. The column widened slightly as it approached the smoke hole, mixing with the surrounding air, but remained coherent and stable. This stability indicated that the air flows converging at the fire were balanced, symmetrical, creating a steady updraft rather than turbulent mixing. That afternoon, I traced the complete circuit. Cold air enters at ground level around the perimeter, is channeled by the liner into the gap, flows downward in the gap, seeking the lowest point, pools and warms at the base, rises through the gap as it becomes buoyant, emerges at the top of the liner into the living space, flows toward the fire drawn by the fire's oxygen demand, rises through the fire heated to extreme temperatures, exits through the smoke hole as hot combustion gases. The cycle was continuous, self-sustaining, driven entirely by temperature differences and density gradients. No fans, no mechanical assistance, just natural convection, working exactly as thermodynamics predicted. The Tipi was a convection engine, converting heat energy into airflow, using that airflow to manage smoke and provide ventilation. By evening, I understood why the double-wall design was essential. A single-wall Tipi would still have convection, hot air would still rise and exit through the smoke hole, but the incoming cold air wouldn't be managed. It would flow chaotically across the floor, creating cold drafts, mixing inefficiently with the warm air, disrupting the smoke column. The liner organized the flow, channeled it, extracted useful work from it, transformed chaotic turbulence into organized circulation. The sixth day, I examined the ground-level details I'd been overlooking, how the teepee cover was secured to the ground, how the air intake gaps were created and controlled, and how these details affected the overall airflow system. I'd assumed the cover was simply staked down with wooden pegs, but the reality was more nuanced. The cover was secured with anchor pins, sharpened wooden stakes about 18 inches long, driven through reinforced grommets in the canvas and into the ground. But the pins weren't driven tight against the canvas. Instead, they were angled outward slightly, creating tension that pulled the cover taut while leaving a controlled gap between canvas and ground. The gap size was determined by how far out the pins were positioned. Pins driven closer to the cover created smaller gaps. Pins driven farther out created larger gaps. Maka Washte showed me the pattern she used: tight at the back where the liner was weighted down, progressively looser toward the sides, and loosest at the front near the entrance. This pattern created an intake distribution that matched the convection pattern, more air entering where the circulation needed it most. The liner's role in intake control became clearer. The liner's lower edge rested on the ground, weighted with stones sewn into pockets along its perimeter. These weights could be adjusted, adding or removing stones to control how tightly the liner sealed against the ground. Tight sealing reduced air intake through the liner channel. Loose sealing increased it. On cold, calm nights, Maka Washte added weights, sealing the liner tightly and forcing most air intake to occur at the front near the entrance. This minimized cold air infiltration while still providing adequate ventilation for the fire. On windy nights, she removed weights on the windward side, allowing more air to enter the liner channel, increasing the convection current to help combat wind-driven pressure fluctuations. I measured the intake area under different configurations. With the liner tightly weighted, total intake area was perhaps 3 square feet, mostly concentrated at the front. With the liner loosely weighted, total intake area increased to 8 square feet, distributed around the full perimeter. This 3-to-1 adjustment range allowed the teepee to adapt to vastly different conditions while maintaining adequate ventilation. The relationship between intake area and draft strength followed fluid dynamics principles. Smaller intake area increased air velocity as it entered. The same volume of air had to flow through a smaller opening, so it moved faster. Faster moving air created stronger circulation currents, pulled smoke out more effectively. Larger intake area decreased velocity, but increased total volume, providing more oxygen for combustion and breathing. That afternoon, I experimented with different anchor pin configurations. I repositioned pins to create very small intake gaps, then built up the fire. The draft was strong, smoke exited cleanly, flames burned vigorously, but the fire consumed wood quickly, drawing excessive air. I repositioned pins to create larger gaps, rebuilt the fire. The draft was gentler, flames steadier, wood consumption more moderate. The optimal configuration depended on multiple factors: outside temperature, wind conditions, fire size, and occupancy. Cold temperatures required smaller intake to minimize heat loss. High winds required larger intake on the leeward side to prevent smoke from being pushed back down the smoke hole. Large fires required more air than small fires. More people required more ventilation than fewer people. Maka Washte explained that experienced teepee users adjusted the anchor pins daily, sometimes multiple times per day, in response to changing conditions. The adjustments were small, moving a pin an inch or two outward or inward, but the cumulative effect was significant. The teepee's performance could be fine-tuned through these small adjustments, optimizing for current conditions rather than accepting a fixed configuration. The entrance area received special attention. The entrance flap, a separate piece of canvas that covered the doorway opening, could be rolled up for access or dropped down for closure, but even when dropped, the flap didn't seal completely. There was a deliberate gap at the bottom sized to provide air intake for the fire even when the entrance was closed for sleeping or weather protection. This entrance gap was the primary intake when the liner was heavily weighted. Air would flow in through the gap, across the floor toward the fire, be heated and consumed, then exit as combustion gases. The flow path was short and direct, providing immediate oxygen to the fire without complex circulation through the liner channel. By evening, I understood that the anchor pins and intake gaps were not afterthoughts or simple functional necessities. They were adjustable control points, tunable elements that allowed the teepee's airflow system to adapt to varying conditions. The system wasn't fixed. It was flexible, responsive, capable of optimization through small but thoughtful adjustments. The seventh day brought conditions I'd been dreading: a severe windstorm, gusting above 50 miles per hour, with winds shifting unpredictably from northwest to northeast and back. Rain began in the afternoon, driven horizontal by the wind, soaking everything outside. I expected disaster, smoke-filled chaos, collapsed structure, miserable conditions, but Makawashte seemed unconcerned. She checked the anchor pins, adjusted a few that seemed loose, repositioned the liner weight slightly, and settled in to work on beadwork as if the storm were irrelevant. I watched the teepee cover billow and snap in the wind, watched rain stream down the canvas, and waited for the inevitable failure. It didn't come. The smoke continued exiting cleanly despite the wind. The structure remained stable despite the gusts. The interior stayed comfortable despite the storm outside. I was witnessing the teepee's design intention. This structure was built for exactly these conditions, for the unpredictable, violent weather of the plains. The wind direction shifted from northwest to north, and I jumped to adjust the smoke flaps. Makawashte gestured for me to wait, to watch. The smoke column wavered as the wind shifted, dispersed briefly, then reformed as the new wind direction established itself. Within 30 seconds, the smoke was exiting cleanly again, pulled out by the Venturi effect created by the north wind flowing over the repositioned landscape of the smoke hole. She let me adjust the flaps after the smoke stabilized, teaching me to wait for wind direction to settle before responding. Premature adjustment could make things worse, she explained. Better to let the system adapt naturally than optimize once the new conditions were stable. The Tipi was self-correcting to a degree. My job was to assist it, not force it. As the storm intensified, I noticed the convection system was working harder. More air was entering through the intake gaps, driven by wind pressure on the windward side. But the liner was managing this increased flow, channeling it, preventing it from disrupting the living space. The fire burned hot, consuming the extra oxygen, producing more heat that was needed to maintain comfort, as cold wind increased heat loss through the cover. The rain-soaked canvas revealed another design feature I hadn't anticipated: wet canvas swells, tightening the weave, reducing air permeability. The outer cover, which had been slightly porous when dry, became nearly airtight when wet. This sealing reduced infiltration, reduced heat loss, actually improved the teepee's thermal performance despite the rain. The gaps between poles where the canvas draped also sealed when wet. Dry canvas had small gaps where it draped. Wet canvas swelled and filled these gaps, creating a more complete envelope. The structure became tighter, more wind-resistant, more thermally efficient as it got wetter. Counterintuitive, but highly functional. That afternoon, a particularly strong gust hit the teepee. I estimated 60 miles per hour, and the entire structure leaned noticeably. The poles flexed, the canvas billowed inward on one side, and I thought surely this would be the collapse. But the teepee recovered immediately, the poles springing back to vertical, the canvas tensioning itself. The structure was flexible, designed to bend rather than resist, to absorb energy rather than oppose it. Makawashte explained the pole configuration. The poles weren't rigidly connected. They rested against each other at the peak, held in place by the canvas cover wrapped around them, and by tension from the anchor pins at the base. This loose connection allowed independent movement. Each pole could flex and shift without forcing the others to follow. The structure was articulated, dynamic, able to respond to localized forces without transmitting stress throughout. As evening approached and the storm continued, I realized the teepee wasn't just surviving the conditions, it was functioning well in them. The smoke management was actually better than it had been in calm weather. The strong wind created stronger venturi effect, pulled smoke out more vigorously. The fire burned cleanly, provided ample heat, required no special attention. Inside, we were comfortable, dry, warm. While outside, the storm raged. By the time the storm passed after midnight, I'd learned a crucial lesson. The teepee was designed for worst-case conditions, not ideal conditions. The design assumptions were severe wind, driving rain, rapid weather changes, the reality of Plains life. In these conditions, the teepee excelled. In calm, mild weather, it was over-engineered, more capable than necessary. But that over-capability meant it never failed when conditions worsened. The 8th morning, the storm had passed, but everything was soaked. The teepee cover dripped with water, the ground was saturated, and I expected cold, damp, miserable conditions as the structure dried. Instead, I woke warm and comfortable, with the interior air dry and fresh despite the sodden canvas overhead. I examined the outer cover carefully. Water had soaked completely through the canvas. It was saturated, heavy with absorbed moisture. But the inner surface of the cover, where I expected to find condensation dripping, was barely damp. Most of the absorbed water was staying in the canvas fibers rather than dripping or evaporating into the interior air. The liner explained this. The liner hung several inches inside the wet outer cover, creating an air gap. Water evaporating from the inner surface of the outer cover was moving into this gap, not into the living space. The air in the gap was cooler than the living space air, perhaps 45 degrees compared to 60 degrees, so moisture condensed on the outer surface of the liner rather than entering the living space. I checked the liner's outer surface and found it was damp, but not dripping. The moisture was condensing as small droplets that ran down the canvas and dripped to the ground at the liner's base, outside the living space. The liner was capturing moisture, preventing it from entering the air we breathed, keeping the interior environment dry despite the saturated outer cover. This moisture management extended to the floor. Water running down the liner dripped at the liner's base into the gap between liner and outer cover, where it soaked into the ground or ran outward toward the teepee perimeter. The floor inside the liner, the actual living space, remained dry. The liner created a moisture barrier, a drainage system that kept the occupied space comfortable even when the structure itself was wet. But the wet canvas provided advantages beyond just not failing. The swollen fibers had sealed air gaps, as I'd noticed during the storm. Now, in the calm morning, this sealing remained, creating a tighter structure with less air infiltration. Heat loss was reduced. The fire required less fuel to maintain interior temperature. The teepee was actually more thermally efficient wet than dry. I measured the difference with my thermometer. With the cover dry, as it had been earlier in the week, the interior temperature with a moderate fire was roughly 58 degrees, while outside was 38, a 20-degree differential. With the cover wet, the interior reached 63 degrees with the same fire size, while outside was 36, a 27-degree differential. The wet canvas was providing roughly 35% better thermal performance. The physics were straightforward. Dry canvas has small gaps between fibers where air can pass through. These gaps allow infiltration, outside air seeping in, inside air seeping out, bypassing the insulation value of the canvas itself. Wet canvas swells. The fibers expand and press against each other, closing the gaps, creating an airtight barrier. Infiltration drops nearly to zero. All heat loss occurs through conduction and radiation rather than convection. That afternoon, as the cover began to dry in the sun, I watched the thermal performance gradually decline back toward the dry baseline. The canvas fibers were shrinking, gaps reopening, infiltration increasing. By evening, the cover was mostly dry, and performance had returned to the dry level. The wet advantage was temporary, lasting only while moisture remained in the fibers. But temporary didn't mean unimportant. On the plains, where storms were common and canvas frequently got wet, this performance boost during and after storms meant the Tipi was most efficient exactly when conditions were most challenging. When it was cold and wet outside, when heat loss was greatest, the structure's thermal performance improved to compensate. The design turned a potential weakness, absorbing water, into an operational advantage. Makawashite explained that experienced Tipi users understood this wet advantage and sometimes deliberately wetted their covers in winter. A bucket of water splashed on the windward side would soak that section, seal it, reduce heat loss through infiltration. The cover would dry over days, but the temporary sealing provided immediate comfort improvement, especially during extended cold snaps. I also learned about the cover material itself. The canvas wasn't modern woven cotton, it was buffalo hide, tanned and smoked, sewn into large panels. Buffalo hide had different properties than canvas: better water resistance, better durability, different shrinking and swelling behavior. The lodge I was studying had a canvas cover because buffalo were becoming scarce, but Makawashite said the principles were the same. Both materials sealed when wet. Both provided the thermal advantage. By evening, the cover had fully dried, stiff in the cold air, and I documented the complete wet-to-dry performance cycle. The Tipi wasn't just weather-resistant, it was weather-adaptive, performing differently under different conditions, always optimizing for immediate circumstances, rather than accepting fixed performance across all conditions. The 9th day, I studied the liner's geometry at its base, where it met the floor. I'd noticed the liner didn't hang vertically. Its lower section angled outward, creating a curved surface that directed something, though I wasn't initially sure what. Makawashite explained it was for heat, for directing the fire's warmth toward the people rather than letting it escape through the walls. I examined the angle carefully. The liner hung vertically from about 5 feet down to about 18 inches above the floor, then curved outward at roughly 45 degrees for the final 18 inches to the ground. This created a concave surface facing the living space, like a partial cone or funnel, with the narrow end at the floor and the wide end at the point where the liner became vertical. The fire sat in the center, radiating heat in all directions. Heat radiating toward the outer walls would strike the liner's curved lower section and be reflected, not perfectly like a mirror, but partially redirected inward and upward toward the occupants, rather than continuing outward toward the cold outer cover. I tested this with my hand, holding it at various positions. Sitting on the floor 2 feet from the fire, I could feel warmth on my face and chest, direct radiation from the fire. But I could also feel warmth on my back, even though my back was facing away from the fire. This warmth was coming from the liner behind me, reflected heat that had radiated from the fire, struck the liner's curved surface behind me, and been redirected toward my back. The reflection wasn't complete. Perhaps 30 to 40% of the radiant energy was reflected, with the rest absorbed by the canvas or transmitted through it. But even partial reflection was significant. It meant heat was being directed toward the living space rather than wasted warming the structure's outer layers. I calculated the geometric advantage. With a vertical liner, heat radiating from the fire would strike the liner at 90 degrees, be mostly absorbed, conduct through the canvas to the outer cover, and be lost. With the angled liner, heat struck at roughly 45 degrees was partially reflected back toward the center, made a second pass through the living space before eventually being absorbed. This double pass increased the useful work extracted from each unit of radiated heat. The curved geometry also created a focusing effect. Heat reflecting from the far side of the teepee would converge toward the center and lower areas, where people sat and slept. The liner was acting as a parabolic reflector, concentrating heat where it was needed rather than distributing it evenly throughout the volume. That afternoon I compared comfort at floor level versus higher up. Sitting on the floor, I felt warm, comfortable, adequate heat from the fire. Standing up, head near the peak, I felt cooler, despite hot air rising to the peak. The standing position removed me from the reflected heat zone. Only direct radiation reached me. The floor level was optimized for comfort, while higher elevations were deliberately less comfortable, encouraging people to sit or lie down where heat was concentrated. The liner's canvas material contributed to reflection. Canvas, especially when slightly soiled from smoke and use, had a matte but somewhat reflective surface. It wasn't a mirror, but it wasn't a perfect absorber either. Perhaps 30% reflection, as I'd estimated, with the remainder absorbed and either conducted through the canvas or radiated from the canvas's back surface into the gap between liner and outer cover. The heat conducted through the liner contributed to the convection system. The liner's inner surface, warmed by absorbed radiation, heated the air in contact with it. This air became buoyant and rose along the liner surface, contributing to the circulation in the gap between liner and outer cover. The liner was simultaneously reflecting some heat toward the occupants and using absorbed heat to drive convection, dual function from a single element. Makawashite showed me how people positioned themselves relative to the liner for maximum comfort. Sleeping positions were arranged in a circle around the fire, heads near the liner's curved base where reflected heat was strongest, feet toward the fire where direct radiation was strongest. This positioning captured both direct and reflected heat, maximizing comfort while minimizing the fire size needed. By evening, I understood that the liner's lower curve wasn't decorative or incidental. It was deliberate geometry, calculated to reflect radiant heat toward the living zone, to concentrate warmth where people sat and slept, to extract maximum useful heating from minimal fire size. The liner was simultaneously an airflow manager, moisture barrier, and heat reflector, multiple functions from one carefully shaped canvas element. The 10th morning, my time with Makawashite and her teepee was ending. I'd documented every dimension, every technique, every principle that made the structure function. But more than technical knowledge, I'd gained understanding of a different approach to shelter, not static protection from environment, but dynamic interaction with it. The teepee wasn't built to fight the wind, it was built to use wind. The smoke flaps turned wind into an ally, creating suction that improved draft, rather than trying to block wind entirely. The structure's flexibility allowed it to bend with gusts rather than resisting them. The design assumed wind and optimized for it rather than treating it as an unwelcome intrusion. Similarly, the teepee didn't fight rain. The wet canvas sealed gaps, improved thermal performance, turned precipitation into an advantage. The liner captured moisture, prevented it from entering the living space, managed it through passive drainage. The structure worked with rain rather than merely defending against it. Even the fire, typically a source of smoke problems in enclosed structures, was managed through cooperation rather than containment. The convection system used fire heat to drive circulation, which provided the fire with oxygen, which sustained combustion, which drove more circulation. The system was self-reinforcing, with each element supporting the others. I thought about the dismissive term I'd heard used for tipis, just a tent. A tent was static. You set it up, stakes it down, and it either works or it doesn't. You can't adjust its performance, can't tune it to conditions, can't optimize it. A tent functions the same in wind or calm, in rain or dry, in cold or warm. Its performance is fixed. The teepee was nothing like a tent. It was a dynamic system with multiple adjustable elements, smoke flaps, liner weights, anchor pins, entrance configuration. Each element could be tuned independently or in coordination with others. The structure responded to conditions, adapted, optimized continuously rather than accepting fixed performance. The sophistication went beyond just adjustability. The Tipi integrated multiple physical principles: convection for airflow, reflection for heat distribution, venturi effect for smoke exhaust, flexible structure for wind resistance, moisture management for envelope sealing. Each principle was exploited through careful geometry and material selection. The structure wasn't just using one clever trick, it was orchestrating multiple phenomena into a coherent system. I reviewed my calculations from the week. The Tipi, with a moderate fire, maintained a 20 to 25 degree temperature differential between inside and outside, while consuming perhaps 1/10 the fuel a cabin of equivalent volume would require. The smoke management worked reliably across wind directions from calm to 50-mile-per-hour gusts. The structure supported its own weight plus the weight of a wet cover, roughly 400 pounds total, with 17 poles leaning against each other without rigid connections. The numbers demonstrated performance that rivaled or exceeded modern portable shelter. Military tents used in the same period were miserable in wind, leaked in rain, required external stoves that were smoky and inefficient. Canvas wall tents, the best portable shelter European technology offered, still couldn't manage smoke well, couldn't adapt to wind, couldn't maintain comfort in severe weather. But the Tipi's advantage wasn't just performance, it was knowledge, accumulated understanding passed down through generations, refined through observation, optimized through necessity. The people who developed the Tipi lived on the plains year-round, experienced every weather extreme, couldn't retreat to permanent shelter when conditions worsened. The Tipi had to work reliably, had to work in the worst conditions they'd encounter. Centuries of feedback refined the design to its current form. That afternoon, I helped Makawashte dismantle the Tipi, preparing to move camp. The process took less than an hour, removing anchor pins, dropping the cover, separating the poles, folding everything for transport. The Tipi that had sheltered us comfortably for 10 days packed onto a horse-drawn travois, weighing perhaps 150 pounds for the cover, poles, and liner combined. This portability was essential for nomadic life, yet it didn't compromise performance. The Tipi was simultaneously portable and effective, simple and sophisticated. As we folded the liner, I noticed wear patterns, areas where the canvas was thin from use, places where repairs had been sewn. The liner was years old, had sheltered multiple families, had been adjusted and modified countless times. It was a living document of accumulated wisdom, with each repair and modification representing a lesson learned, a problem solved, a principle applied. Makawashte saw me studying the liner and smiled. "The Tipi teaches," she said through the translator. "Every time you use it, you learn something new. The smoke tells you about wind and pressure. The fire tells you about air and heat. The canvas tells you about water and sealing. If you pay attention, the Tipi shows you how the world works, not through words, but through experience, through cause and effect, through success and failure." I understood then that the Tipi was more than shelter. It was a teaching tool, an interface between people and environment, a way of learning about wind and heat and moisture through direct observation. Living in a Tipi required attention, awareness, responsiveness, qualities that translated to success in plains life generally. The skills learned managing smoke flaps applied to reading weather, tracking game, anticipating seasonal changes. As I prepared to leave, returning to settlements and permanent structures, I knew I'd never think of portable shelter the same way. The Tipi had demonstrated that sophisticated engineering could emerge from observation and iteration without formal calculation, that dynamic systems could outperform static ones, that working with environment rather than against it produced better results with less resource input. The double wall that I'd initially dismissed as simple redundancy was actually the key to everything, creating the convection system that managed smoke, pre-warmed incoming air, reflected heat toward occupants, and captured moisture. The liner transformed a simple conical tent into a sophisticated environmental control system, all through passive geometry and material properties, without moving parts or complex mechanisms. Everyone thought the Tipi was just a tent until they saw how it managed a blinding smoke storm. But the truth was deeper. The Tipi wasn't just managing smoke, it was demonstrating a complete alternative approach to shelter, one that embraced complexity, celebrated adaptability, and achieved excellence through working with natural forces rather than opposing them. That was the real lesson, the knowledge worth carrying forward, not just how the Tipi worked, but why that way of working represented wisdom worth respecting and learning from.